Hello and welcome to Unit 11. In this unit we will be studying cosmology, and cosmology is sort of the study of the cosmos, of the distant universe. So if we're going to study the distant universe, there are two things that we need to cover first. So that's what we'll be doing in this mini lecture. The distance ladder, which is how we tell distances to other galaxies, and the expanding universe, which is crucial to grasp in order to understand what is going on when we look at other galaxies. And this material is covered in Chapter 24, sections a little bit in Section 2, more in Section 3, and in Chapter 26, Section 2. So our outline for this mini lecture is to talk about how we measure distances to galaxies. We've already talked about a few pieces of this ladder, how we get distances to nearby stars and to star clusters and the things. And then we'll flesh it out into a full-blown distance ladder, and I'll explain what I mean by that in a bit. Then we will talk about Edwin Hubble and his discoveries of measuring distances to other galaxies, how that work has been carried on with the Hubble Space Telescope, and then try and build that into an understanding of the expansion of the universe. If you try and climb a ladder, let's say you want to go up to the roof of your house, you typically will climb it one step at a time. If you instantly try and climb onto the top rung of the ladder, chances are you aren't going to make it. And if one of the rungs of the ladder is not very strong or hasn't been built very well, and you step on it, it may break and you will fall down and not be able to get to the top. There's a similar analogy for measuring distances to astronomical objects, and that is that there's no one method that can get us every single distance, whether it be things in our own galaxy versus things all the way across the universe. So we have to build upon several methods of getting distances, and we also need to double check each of these methods, cross-reference them, make sure that they give consistent answers so that we know it's a strong step on our ladder on measuring the most distant objects. So we begin with the smallest distances that we need to measure, and that's distances within our own solar system. There are different ways to measure distances within our solar system, but the two primary ways, the most direct ways, are by radar ranging, where you emit a radar beam, it bounces off another planet or an asteroid, comes back to us. We time how long it takes, we know the speed of light, that tells us the distance to the object. And for the moon, we can use laser ranging. Astronauts put mirrors on the moon that will reflect any light that comes into them. And so here's a picture of a laser at McDonald Observatory bouncing off, in this case, a satellite, not the moon, but it bounces off a reflector, comes back to us. That gives us a very precise measurement of the distance down to a fraction of a millimeter. So using these methods of measuring distances, we know the size of our solar system, such as the size of Earth's orbit around the sun, the distances to other planets, the distances to the sun. Now, once we know the size of Earth's orbit, we will use that as our rung for going to more distant things. So if we're getting distances to stars, there's no way that we can bounce radar off of them or lasers off of them. It would take years for the round trip, and the return signal would be way too weak to detect. And so for nearby stars, we use parallax, which we've already talked about. That as the Earth goes around the sun, we get a slightly different view of where a star is. And by measuring the angle of how much the star appears to shift, we can get its distance. That only works as long as you know the size of an astronomical unit, which we figured out in the previous step. And this is pure geometry, so once you know the size of an astronomical unit, you know these distances. And this method of getting distances allowed us to calculate absolute magnitudes and create the Hertzsprung-Russell diagram. Now we're going to use the Hertzsprung-Russell diagram to get distances to other things such as star clusters. When you saw Hertzsprung-Russell diagrams of star clusters, you saw that we had the main sequence on there. Now when we look at a star cluster, we see the apparent magnitude, how bright the stars appear to be, and for a star cluster, all the stars are the same distance away, so they all are made fainter by the same amount. Their apparent magnitudes all go down by the same amount. So if we know where the main sequence should be from the calibrated Hertzsprung-Russell diagram, in other words, we know the absolute magnitudes of stars, and we measure the apparent magnitudes of a cluster, the difference between that main sequence is due to the distance to the star cluster. So by using this technique called main sequence fitting, we can determine the distances to star clusters that are too far away for us to do parallax. Once we have star cluster distances, in some of these star clusters we will find Cepheid variable stars and RR Lyrae stars, and we can use those to calibrate the Leavitt law, because now we have Cepheids or RR Lyraes that we can see and measure their periods in star clusters that we know the distances to. And so, since we know the distances, we can calibrate the luminosities of these, which allows us to calibrate this Leavitt law diagram. And then when we go and look at more distant objects where we can see RR Lyraes and Cepheids but we can't see the main sequence, we can still use this method to get distances. And there are other methods that we can use as we go further out into the universe. So all of these calibrated distance indicators is called the distance ladder because we climb one step at a time. Now I don't expect you to memorize this. This is sort of the distance ladder as it stood a few years ago. And notice that there are several paths, and these paths often cross each other, which means that these can be cross-correlated, cross-calibrated, checked against each other, and we are fairly certain that we understand this entire distance ladder and that it's a fairly firm ladder and we can trust the distances that we get. So if you look at the far left, you can see what we were just talking about. At the very bottom you see the pi, that means parallax. So we get parallax to stars, and then we get that allows us to get distances to star clusters like the Pleiades, which allows us to get distances to Cepheid stars in clusters. And then you see from there we go into Cepheid stars in other galaxies. So as we'll talk about, Edwin Hubble used Cepheids visible in neighbor galaxies of the Milky Way to get their distances. There comes a distance limit where even Cepheid stars are no longer visible with the Hubble Space Telescope, so we have other methods. And we will talk about one of those, which is using a certain type of supernova, in our next mini lecture. The first distances to other galaxies were measured by Edwin Hubble. In 1924, Edwin Hubble was studying the Andromeda Galaxy, and remember that at the time astronomers thought these were just called these nebulae, and there was an argument as to what they were. And Edwin Hubble found Cepheid stars in it. Here is a plot of a Cepheid variable in Andromeda, and you can see it changing in brightness here over a period of about 30 days or so. Hubble was able to determine its period, and therefore he knew its luminosity. He had its apparent magnitude. This PG magnitude means photographic magnitude. That's what they called apparent magnitudes then. So he had an apparent magnitude, he had a luminosity that allowed him to get a distance, and the distance that he got was 220,000 parsecs, which is well outside the size of the Milky Way. Shapley's Milky Way was about 100,000 light years or 30,000 parsecs across, and this was 10 times further than that. Hubble didn't have this quite right. There were some errors in his calibration that we've since corrected, and we know that the distance to the Andromeda Galaxy is more like 700,000 parsecs, 2 million light years. The Hubble telescope, when it was built, one of its primary purposes was to detect Cepheid stars in as many galaxies as possible. This allows us to get a better statistical sample, which allows us to better calibrate distance measures we will use in looking at more distant objects. And so here's a picture on the left that the Hubble Space Telescope took of a spiral galaxy called Messier 100, and on the right it's a close-up of a very tiny region in the picture on the left, and you can see an individual star in this galaxy Messier 100, and you notice that it gets fainter over time between April 23rd and May 9th, sort of hits bottom at May 9th, May 16th, and then it gets brighter again by the end of May. So by watching several Cepheid stars like this, the Hubble Space Telescope was able to find dozens of Cepheid stars in each galaxy, and then by having dozens of galaxies with Cepheid stars, we can get very good statistics on distances. Now, we talked about in our last unit how prior to our understanding of galaxies, astronomers had noticed that most of these spiral nebulae had redshifted spectra. They had Doppler shifts that showed they were moving away from the solar system. In 1929, Edwin Hubble found that these redshifts, these Doppler shifts, depended on the distance of a galaxy. The more distant it was, the greater the redshift. Up at the top, there is a galaxy in the Virgo cluster of galaxies, the nearest cluster of galaxies to the solar system. It has a redshift of about 1,200 kilometers a second, and there are two strong lines that are visible in elliptical galaxies caused by calcium, and they're indicated here by blue. So you can't really see it in the spectrum, which is that bit there on the right, but there are two dips in the spectrum, two areas where it's dark, that are absorption lines due to calcium. If we go to a more distant elliptical galaxy, such as one in Ursa Major, you can see that those two calcium lines have moved toward the red end of the spectrum. This is a redshift, and so we can get its speed, 15,000 kilometers a second. Go to a more distant galaxy, such as one in a galaxy cluster in Corona Borealis, and it's a little harder to see those two calcium lines, but they're still there, even more redshifted. Go to a more distant galaxy cluster in Boötes. You see that the lines are really redshifted, and by the time you get to a galaxy cluster in Hydra, the lines are extremely redshifted toward the very red end of the spectrum. Hubble made a plot of all these galaxies, their distances that he got from Cepheids, and their speed at which they were moving away from us, and he found that it made nearly a straight line. So here on the right is a diagram. We call this a Hubble diagram. We plot distance. The distance here, the unit is megaparsec. 1 megaparsec is 1 million parsecs, or 3 million light years. And then on the y-axis we have the Doppler shift, the velocity in kilometers per second, and all of these are moving away from us. And you see that the more distant you go, the faster the velocity, and you get a nice straight line. So if we write an equation for this line, we find that the velocity of the galaxy is the slope of the line that the galaxies are making times their distance, and we call this slope, we call this Hubble's constant. And so we get an equation that the velocity of a galaxy is equal to this h naught, which is what we mean by an h with a small zero next to it, h naught times the distance. The whole point of this is that more distant galaxies move away more rapidly, and the best measurements of the Hubble constant give a value of really close to 70 kilometers per second per megaparsec. In other words, if a galaxy is 1 megaparsec away, it will be moving away from us at 70 kilometers per second. If it's 2 megaparsecs away, it will be moving away from us at 140 kilometers per second. If it's 10 megaparsecs away, it will be moving away from us at 700 kilometers per second, and so on and so on. This begs the question, what causes this sort of thing? What would cause a more distant galaxy to move away from us faster? And the first thing you might think of is, well, if we're at the middle and everything's blowing up like it's going away from us, this is exactly what you would see. But if there's one thing we've learned in the history of astronomy, it's that any time you think you're at the middle of something, you're probably wrong. We used to think we were at the center of the solar system, but it turns out the Earth goes around the sun. So then people used to think that the sun was the center of the universe, or what we would now call the galaxy. But now we know the sun's most of the way out and goes around the galaxy. So it would be going against all the lessons of history to assume that our galaxy, our Milky Way, is at the very center of the universe. This type of law, this type of Hubble's law, can also be explained with an analogy. Here we have a picture of some raisin bread. If you've ever made homemade bread, you know that you make the dough, you sit, you let it rise, and as it rises it gets bigger. So if you make raisin bread and you put raisins in the loaf, the raisins, as the loaf gets bigger, the raisins will appear to move away from each other. So here we show arrows from one raisin to two other raisins, and you see that as the loaf has doubled in size, the distance between that one raisin and all the other ones has doubled. And if you pick any other raisin in the loaf, you would find the same thing. For example, let's pick this one here. On the left, when the loaf is small, you see that the distances are small. And on the right, after the loaf has grown, all of the other raisins are further away from this one. So in other words, that raisin would see all the other raisins in the loaf moving away from it. In fact, it doesn't matter which raisin you pick in this loaf of bread, all the other raisins appear to be moving away from it. So what this implies is that we can explain Hubble's law without needing the universe to have a center. Just think of a balloon. If you had to live on the surface of a balloon, the surface of a balloon has no center. If I ask you what's the center of the surface of a balloon, you'd look at me funny. You might say, well, the middle of the balloon. But if we had to live on the surface, we can't get to that middle of the balloon. And as you inflate a balloon, it would stretch and everything on that balloon would appear to move away from us. This is what led astronomers to realize that the universe is expanding. And what's going on, it's not that the galaxies are moving through space further away from each other. Just like in this raisin bread, it's not that the raisins are moving through the dough to get further away from each other. It's that space, or dough, itself is growing, and that carries it along. The galaxies don't grow in size because the gravity of a galaxy holds it together, just like the stickiness of a raisin holds it together. So as the dough around it stretches, the raisin doesn't get pulled apart. Same thing happens with galaxies. As space expands, gravity keeps a galaxy the same size and doesn't allow the galaxy to expand. So I have another video below by another astronomer who tries to explain these concepts a little further, and I'd urge you to watch it. A summary for what we've learned in this mini lecture is that we have this thing called the distance ladder that we use to get distances to more and more distant objects. And when we measure the distances of these galaxies, and we also compare it with that apparent Doppler shift, that redshift that we see, that all the galaxies seem to be moving away from us, we find that the more distant galaxies are moving faster than nearby galaxies. And the easiest way to explain this, that doesn't require putting us at the center of the universe, is that space itself is expanding and carrying the galaxies along for a ride. And it wouldn't matter which galaxy you were on in the universe, you would see all the other galaxies moving away from you in this picture. So this completes the first mini lecture for this unit. Think about this stuff, watch the second video, try the responses, and then we'll go on and we will talk about dark energy in the second mini lecture.